All right, this seems like a good point to get started. Everybody, welcome. My name is Robert Stone, and I'm going to be I'm going to move a lot. Just go wide. I'm sorry. I can't help it. Just, okay. So, my name is Robert Stone, and here we are at GAPC, TPC, I'm not sure what it's called anymore, and I'm Dr. Zigman on pause, and I'm from Brainstorming Incubator. And today, we're going to be covering solving WordBrain. It's a breadth-first search of a problem with great depth. Quick little overview before we get started, let you know what we're going to be covering. Slide over a bit, there we go. We're going to take a quick look at two different types of search algorithms. We'll talk about breadth-first versus depth-first search really quick. Okay? Then we're going to go into the gameplay that's involved inside of WordBrain. Now, whenever I think about a mobile game, I always think about the zombie apocalypse. You all thought it was going to be like The Walking Dead, and it's just people on their phones everywhere. So, whatever we can do to really, beat that with our own zombie creations, we're going to be in good shape. We're going to talk about the object of the game. Oh, in case you weren't aware, WordBrain's a game. Yeah? Okay, cool. We're going to talk about the object of the game. We'll talk about the rules, how the game is played, and then we're going to cover some caveats that make the game a little bit more challenging and harder to program than you might have ordinarily or initially thought. Next, we're going to cover actually solving WordBrain. And in here, we're going to focus on first how to model the problem. Whatever games you're trying to solve, or really any problems that you face as a developer, it really comes down to your ability to model the problem. Take a large problem, break it down into smaller pieces. So we'll cover that very briefly. Then we'll talk about the solve method and the WordBrain solver itself. And then we'll talk about running the solver. I'll show you how it did, some runtime, some solutions, that kind of stuff. Then we're going to focus on performance. And I'm just going to back up for a quick second. I have quite a bit of code for the solving WordBrain that's part of the slides. Kind of depending on how we're doing time-wise, I might skip through them pretty fast. And if that happens, I apologize, but I'll make them all available online. I just, there's a lot of good stuff at the end I want to make it to, and it's a lot of dense material to run through. So we're just gonna fly. We'll talk about performance. We'll talk about NYTProf. Anybody who works with me knows that you can tell me something, and I don't believe you unless you can prove it to me with NYTProf. I want to see the performance. And then we'll talk about some potential future ideas. We do implement some of them. Okay, but there are other ones we'll focus on as well. So, just a real quick introduction to two different types of search algorithms. We have first the concept of depth-first search. And as you might imagine, with a name like depth-first, we're going to go all the way down, working our way. We're going to do the depth aspect first. Then we back up and come back down. And you'll see, and I'm kind of just going through it, this is the procedure for a depth-first search. And the numbers are just like you would expect it. Number 1, then 2, then 3, then 4, then 5, so on. Contrast this to breadth-first search. In this case, we're going to start at the top here, and we're going to go here to 2, then back up to 3, and then 4. We see the real difference here. Depth-first all the way down, breadth-first, talk to my neighbors first. Okay? Just a little bit of terminology. It's probably something most of you are already familiar with. We got some more animation. Great stuff. Okay. Let's talk about the game, the gameplay itself. How do you play? Well, the very first thing you'll notice when you play the game is you have a grid of letters. And what's kind of funny, you guys will see, I was originally working on this around Valentine's Day, because I'm that cool. So you'll see these little hearts everywhere because they kind of try to do it up for the holiday. So you'll see those. First, we have a grid of letters. Now, this grid of letters can range from a 2x2 grid all the way up to an 8x8 grid. And as you can imagine, more letters, the harder problems. In addition to that, we're given a list of words we have to find. That's what this equates to down here. And what that's made up of are the letters that are comprised in here. And what we're told is the number of words that we have to find and the length of each word. Okay? It's not always one word, they're not always 4 letters. It will always total. So if there's 4 up here, there'll be 4 down here. So it does always sum, but it does vary. The letters from the grid that's these grids right here, they actually comprise that word. What's important is that there is only one right solution for here. Okay? You might actually be able to spell out 15 different words with the letters given, but there really only is one answer that the game will accept. Great, great, great. There is no time limit, which is always nice. And you do have a limited number of hints. These are these things at the bottom. This is how the makers of the game, I believe it's Mag Interactive, have monetized the game. They have ads too, but you can buy hints. So, you know, I don't like to buy hints, especially when I can, you know, devote hundreds of hours to writing a program to solve it where I don't get my hourly rate. So, I definitely saved $2. I came to a conference with the idea, I should have just bought the hints. So, let's play a quick game, now that we know the general rule. Here we have our grid. First thing we have to do is touch letters for potential words. Now, the thing that's significant here is that the letters must touch in one of the 8 cardinal directions. So, one word that pops out to me right away is book. I see that I can spell out book. B-O-O-K. And if I do that, you can see that's what happens when you select them. They take that color. Now I want to stress again, they have to touch in one of the cardinal directions. Once you've found a word, if the game accepts it, if the word is correct according to the game, the letters are removed. And then what happens is the remaining letters shift down. This is one of those things that makes it kind of tricky to model the game. So what we see, and I'm going to let you see this one more time, that B, K, O, O, those are about to go away, and that O is going to fall down. So when I look at it now, I see that. So the game does change as you're playing. After we do that, we have to keep repeating, selecting words. Does anybody see what the next word is here? Elbow. Yeah, elbow. So we'll select that. It'll get accepted. And once all the words are found, you win. Yay! And it tells you how great you are and how big your brain is. So, you know, it's one of those, the theory where they want to reward you. It's that endorphin release that you get really early in the beginning. And then as the game gets hard, you just want to throw your phone.
Why couldn't the answer be below?
Because the game did not accept it. The game has something that they expect to be the answer. And that's like the #1 problem we face in this. Well, that in computation time. But there is only one accepted answer, even though there are multiple right answers. Okay, sounds easy, right?
Right.
Yeah, it sounds super easy. Caveats. First of all, multiple solutions, but only one accepted one. I know I'm kind of harping on this, but this is a big one. Okay? There's only one accepted solution. The words that you select, not only do you have to get the words right, but you have to select them in the right order. Let me give you an example. I've already solved this, and by I mean the thing I wrote solved it, because I'm not very good at this game. I happen to know that the answers are orange, goat, bullet. Now, if I don't select the letters in the right order, let's say I select orange like this, just like that. If I do it that way, I get stuck. I can't select goat, and I can't select bullet. I have the right answers, I know what they are, but you must select them in the right order because of the way the letters cascade and fall down. Okay, that's another real challenge to this. Just to show you what it would have looked like otherwise, if I would have taken that E instead of that E, in this case, I can spell goat. And once I can spell goat, that goes away, I can spell bullet. So it's significant. You have to select things in the right order. There are multiple ways to select a word, but some methods leave the board unplayable. And when the board's unplayable, you have no choice. You just have to restart. But yeah, the letters must be touching. So you can't skip around. You have to be touching in one of the cardinal directions. We're doing okay for time. So modeling the problem. Probably the first stage, one of the harder things to do. Well, we have to keep in mind all the different game types, or types is the wrong word, game difficulties. We have to keep track of what the grid is, the number of words that we're trying to find, the letters, the shifting that happens, all that we have to keep in mind. So, I'm going to use my fake ML because I don't really subscribe strongly to UML. I never remember if I'm supposed to use the aggregate or the composite line thing, and one of them has a diamond on one end with a circle. I don't know. So I have like my fake UML, which is very similar to it, but it'll tell you, you get the idea. So the first object we have, excuse me, the first object we have, I'm coming back, you don't have to shift, I'm just getting this. So, is the WordBrain game. And the game, as you might imagine, is literally the entire game. It's the representation. And some of this stuff is small. I'll read the stuff that's super important. It's meant for you because I'm sure you guys can't wait to get home tonight and just read the slides. So, the game itself is comprised of the letters, the words to find, because remember, I know how many I need and how long they are, as well as the solutions, or the possible solutions, because we know that there are multiple solutions. The elbow versus below was a good example of that. We also have a couple of methods. We have the solve method, the construct game without word, which is the fancy way of doing the cascade, and we'll see that in a little bit more detail. And we also have get letter apposition, convenience, because I'm lazy. Then we have the WordBrain letter. Now a letter is comprised entirely of three pieces. The actual letter itself, is it a Q or it can't be a 7, because 7 is not a letter, a W, anything like that, and its position in the grid, its row and its column. In addition to this, we know that we have certain words we must find, the word to find. Pretty simple, all I know about it is the number of letters. That makes for an easy object. Then we have the solution. Now solutions, we can have multiple solutions. Okay, and unfortunately, the only way to figure out which solution is actually correct is to do the swipey stuff on your phone, which sometimes gets to be a little insane when you see later how many solutions there are for certain things. We also have the concept of a word. And a word is really just a collection of letters. Okay, it's just a list of letters, with another convenience method to stringify it. That's got an operator overload, whatever, fancy stuff. I'm going to back up real quick. So these are the key components that make up the game. Now, once we can represent the game in memory and in a computer, we can actually make the program do some work for us. Okay? Let's look at the solve method. I'm kind of, yeah, that's really small for you guys. All right, we're going to be okay. I'm going to focus on the visual aspects of telling you what it does. We won't worry too much about the code itself. Okay? So the solve method. Remember, it's a method of game. And solve, unsurprisingly, determines the solutions. So we have here our game board. And now we're talking for real. This is a 4x4. It gets much harder. With 4x4, that's respectable. You can pull that off. The first thing we do is we want to get the maximum word length. Knowing or looking at these, I want the max word length. The maximum needed word is, I believe that's 8 characters. Yes, I wrote it. 8 characters, okay? Now, the reason that's significant, if I didn't first calculate what the maximum word length was going to be, and I instead looked at what the maximum possible word length would be, I'd start here at F, and we would drag all the way around to every single letter, which would give us a word length of 16 characters. That's a lot of recursion that I don't have to do. That's a ton of calculation that there's no reason to do because the maximum word I want is 8 characters. So, first thing we do, what's the maximum length? Once I do that, let's stop descending and doing more investigation. Okay? Then what we're going to do is for each letter, So we could just start with F. Okay? For each letter, we need to find the words that are near to it. And we're going to look at some detail at how that method works, but for right now, we're just going to say for every letter I have, I need to find all the words that I can build with that letter. So starting with F. I'm just going to do it over here. We have the F. Well, first thing I could do, I could go FL. That's valid. Now, we're not talking about spell checking. Is this an actual word yet? We're just trying to build the collections of letters. So we have FL, FLA, FLAG, blah, blah, blah. So you guys see how we're doing this. FLAG, then we're going to A, R, so on and so on and so on. But this is where it gets interesting. After we've done this S, H, I don't do SHF. I just instead do SF. And the reason being, 8-character maximum. I don't need to go any longer than that. Okay? This just creates a whole bunch of these. And you can take my word for it. Eventually, if you did that, you'd end up with something like this. The next step we have built into this is the search through the possible words. So we have these possible words, candidates. We need to first evaluate, is their length equal to the length of a word that I'm looking for? One letter doesn't match any of these, so that's not going to help me. So we perform that filtration. We find out from that we have flag is a 4-letter word, one of my favorites. Then we have flaggerish. Flaggerish is a 8-letter word. 1, 2, 3, 4, 5, 6, 7. That's 8 letters, right? Yeah, it's 8 letters enough. And we have a couple of other potential candidates that are 8 letters. So we've just narrowed down our solution space a little bit. At least we know the potential letters that we're working with, the potential root words. Now that we have these, we're going to perform the relatively computationally expensive spell check step. I need to know if this is actually a real word. And from that step, tells me flag is the only actual word I was able to find here. And what's nice about that, oh, it didn't show it yet. Flag does happen to actually be one of the answers. So that's how we basically get to the solutions, okay? Obviously, that's very high level. We're going top down, so let's get a little deeper. Okay, this is all stuff you've already seen. Just commented out, trying to save some space. Okay. It's even small for me. I don't know what I was thinking. Okay. So all this comment right here, that's just the stuff we've already discussed. So the next step we have here, for the actual word. Actual words are words that we have spell checked. We have spell checked, we identified this as an actual real word. For each one of those, first we're going to look to see if there are any more words to find. If I only need this one last word, okay? Wasn't me. Then if we go, I think that's them over there. We're fine, right? Everybody's good?
Yep.
Okay. If I have more words to find, I have more work I have to do still. So the first thing we're going to do is we're going to construct a game without the word. That constructs game without word method is what takes care of that cascading down the letters, excluding them, shifting things around. There, I told you flag was going to be the word. Okay? It's almost like I saw it. Now, this is the word, I'm sorry, this is the game constructed without the word. I had to take those letters out. Then, we just call solve on this new, that would be a 3x4 game. It's the same logic, it's the same method. So we just are going to recursively call that until we have all of the game solutions. Now the game solutions, it is an array ref of solutions because there are multiple solutions. We don't know which one's right until we actually try it. Okay? This is just us creating a new solution. And this would be the terminal recursion case, the bottom case, where there are no more words I need to find. I found all the words I need. We just set the solutions and then we move on. Now I know you guys are dying to see this, so I'll share it to you. The actual answer to this is flag, neck, and starfish. I know, you guys' lives are complete now. Okay, so we went through that. We have the find near letters method, which we'll go into a little bit. I kind of want to hurry up a bit and get to the performance aspects because I think you'll enjoy that much more. So find near letters. The way find near letters works is you basically, unsurprisingly, are finding the letters that are near to a specific letter. In this case, we're going to use F. Now, when I have these row offsets, what I'm basically doing is I want to start here and work my way all the way around that letter. So we're just doing a simple set of, or pair of loops, nested loops, to perform that. The first thing we do is we check to see if the offsets are both 0 and 0. If my row offset is 0 and my column offset is 0, I'm at my initial letter. There's nothing to check. So move forward. Then we just have a quick convenience assignment because I don't like to type too much. Then get letter at position. All that does is another convenience method that gets me the letter at any given position in the game. If there is no letter, skip to the next letter. If we've already used the letter, because you can only use each letter once, skip to the next letter. Then we're going to go ahead and return them and so on and so forth. So let's look at this graphically. In this example, I'm going to say S is my root word. Okay, that means it's part of the word that I've already decided I'm starting to build. So the S is already part. And we're looking at F. We want to find all near letters to this F. We're going to populate this little chart as we go. So first off, we have the -1, -1. And when we do that, we see that H is the next closest letter. I'm sorry, is the first near letter. We'll go ahead and just populate that. S we know is our root. We already had S. F is the current letter that we're looking at. And H is the near letter. This is going to repeat. Next, we're going to try to go up. Well, we can't go up. There's no letter there. So when there's no letter there, there's just nothing to happen. It's just next. The same thing's going to happen when we go up to this corner, to the right. Oh, I'm sorry, to the left. Let me back that up a little bit. So going back to the left, we know that we cannot duplicate. So when we try to use S again, it's going to skip it because it's already been used. Okay, we've already done the center. All right, you guys are getting the point here. And we'll just do one last one. So we see we got the FR, FI, and FH. We see all of those right here. So that gives us our near letters. From near letters, we use that to construct the logic for find near words. The find near words method, this is the solve that you've already seen. I'm just truncating it so that you can still see where we are if you're trying to follow along when you're actually looking at code. The find near words method, and you'll see a couple of times, I do comments like no moose X params validate for performance reasons and things like that. You know, I'm a big advocate that you shouldn't micro-optimize and you shouldn't pre-optimize. You know, obviously there's some best practices you want to follow. You know, personally, I use moose X params validate for like everything. Okay? But it turns out to be fairly expensive, which for that reason, you'll see those comments out there. For the find near words, I'm going to get it all up there and we'll talk that way because it's graphical. Okay, and the graphics is going to be a lot easier for you to see. So for the find near words, what we're doing in this case, come on, is we're ultimately ending with this collection, this find near words. And the way we accomplish that is by iterating over near letters. And we just keep building them one letter at a time, one letter at a time. We do perform some sanity checks. We make sure we never go past the maximum length. If the number of letters is greater than the max word length, return what we have because there's no reason to keep recursing. Other than that, it's just continue to call find near letters and glue them on to my root word and return that up the stack. Okay, now we're getting to the fun stuff. Okay, we got to some dry, you know what are we going to do? Let's look at actually running the solver. Well, here is our sample board, and this is how you actually use it. I have changed it since so that you don't have to put the commas in all the time, but initially I kept the commas. Sounds pretty straightforward and easy. When you run it, it will show you what the game looked like in case you forgot, and then it will provide all possible solutions and tell you how to move your finger to get to them. This one actually had two possible solutions. It had the word goat, G-O-A-T, and toga, T-O-G-A. Both are right solutions, but only one of them is correct according to the game. Now, I know the next thing you're going to be interested in is runtime. Not bad, 0.357 seconds. Okay, respectable. I mean, how much worse could it get? So now we have a 3x3 matrix. In this case, we're looking for a 3-letter word and a 1, 2, 3, 4, 5, 6, 6, 7, 8, 9. Yes, a 3-letter and a 6-letter word. Again, we just feed it on in. Now when we do this, shows us the game, you'll notice that we have again two solutions. In this case, we have nuss waffle. I didn't really think nuss was going to be a word it was looking for, but it is a valid English word. And then sun and waffle. And it tells us again how to do it, because it is important. Sometimes you cannot go in a specific order. Based on this, we can then see that our runtime, again, not so bad, 1.648 seconds. And in case you're looking for a hardware match, this is on an AWS small, just regular small instance. Nothing too fancy there. So, okay, let's keep going. Let's see how we're doing here. In this case, we have the 4x4, and we're looking for 3 words: a 4-letter, a 6-letter, and another 6-letter. Well, what's going to be interesting, as you get larger and larger, the solution space actually gets larger. So we're seeing more possible solutions. Now, in this case, the answer, goat, bullet, orange. Not too bad. And the runtime here is 1 minute and 24 seconds. Now, it's not terrible, 1 minute and 24 seconds, but it's not that great. And this is still only a 4x4. And we're still only looking for 3 words. What happens if we get worse? Here's a 4x4, and in this case we need 4 different words. 3, 3, 5, and 5. With more smaller words, the solution space really explodes. In this case, these are all the potential solutions. Okay? Now it turns out that this is the actual solution, and what's nice about the way the solver outputs it, it groups them together. Because if bag is not a word, period, it doesn't matter in which order I use it, it's not a word. So, tries to make it a little easier for you to follow through. But, at the end of the day, that's a lot of solutions. And the part that gets even worse is it took 10 minutes and 53 seconds to calculate these solutions. You know, that's kind of a while. You know, sure, I've seen worse, but you know, we're still only on a 4x4 grid here. Oh, all right. Well, you know, how much worse could it get? Really? Okay. In this case, we have again an instance of 4 different words we're searching for, and really the number of solutions is just outrageous. And I couldn't have a font small enough to put it up there. So I'll just tell you, the actual solution was saw, hen, crow, finger. Whew, those smalls. And this took 27 minutes and 14 seconds to calculate. Okay, we're going to have to do better than that. Okay, we're going to have to, because 27 minutes, nobody's impressed. 27 minutes, you can probably figure it out in your head by hand or something. You know, so we're going to have to step this up a couple notches. The first thing we have to do is we have to look at what is called a flame graph from NYTProf. For anybody who's completely unfamiliar, NYTProf is basically a super fancy and awesome code profile. Okay, it tells you how things are running, how often they're running, how long they're running, so on and so forth. I always look at 2 pieces. Now I know that there's a lot more you can do with NYTProf than what I use it for, but personally, the first thing I look at is the flame graph. And I look for super wide pieces here because that tells me that there's something specific that if I optimize that one piece, I could run a lot faster. Now in this case, unfortunately, there are no major imbalances. You know, nothing is obvious, nothing's jumping out. Typically, if you see like, is all one certain thing, that tells you like, look, person who's not very smart, you need to go in there and optimize that one subroutine. But unfortunately, that's not the case here. What we do have is, or what I do like about this is you can see the recursion in define near words really nicely here. And if you look at how many times we do it, you'll notice that thanks to the limit we put of no more than the maximum number of letters in a specific word solution, we realize that we don't have to recurse 16 times. That'd be really bad. So unfortunately, in this case, the flame graph didn't really help me. So the next thing I will typically look at are the top subroutines. Now these top subroutines will tell us where we spent most of the time in our code. First, we're telling us that operator equality, this specific method, is where we spent a huge amount of our time. So maybe we could optimize it. Maybe we can't optimize it. Not really much we can do with that. Okay, it's a letter equal to a letter, a row to a row, and a column to a column. Ironically, I did actually first have this check the rows and the columns, but by switching it to the letter first, because there's less likelihood of a collision in letters than there are in rows or columns, it did speed it up a little bit, but you're not going to get a ton out of that. We do see that we call list util first quite a bit. But it's list util. You know, it's possible that they went with a non-optimum implementation. And, you know, personally, I think I'm the best developer ever. But he probably did a pretty good job of it. You know, I could take a peek, but really, I can just consider that optimized and nothing I can really do. I do see find near letters. That is called, or I do spend quite a bit of time there in find near letters. And it's not surprising because I do have to keep calling it. I do have to keep looking for near letters. Not too much, so I mean, well, maybe we can get creative. What I do notice are the moose-related methods. And they're kind of hiding you a little bit. We see this anon moose util items right here. We see a destroy, we see a new, we see these calls that, you know, individually the moose calls aren't so bad, but they kind of stack up on you. Okay? And I love moose. You know, I'm a huge fan of it. I use it all the time for like everything that I do, like ever. To the point where I first wrote this solver with moose objects. Turns out that it's kind of expensive to do it that way. So the next thing we did was we went ahead and we pulled out the moosey guts and just switched to straight up Perl object-oriented programming. That's where you do like the sub new, and you have like a hash ref, and you return blessed class, you know, all that kind of fun stuff that, you know, it's not something I do often because I love moose so much, but we did go ahead, we made that change. Once we make that change, we can take another look at the flame graph, and I gotta say, as much as I still love moose, sometimes it's expensive, and it's not always the 100% choice, but I mean, it's almost always worth it. And I mean, sometimes you just have to know your role. No, nothing, none of this crowd. Don't object. Okay, yeah. But really, we do see that there's a slight shift in time, or a slight shift in where time is being spent. We're doing over. Speaking of time. We notice that we do not see any of that moose stuff anymore. We still see the new, you know, but that's not too bad. But we are saving some time. We see that find near letters is our #1 offender. Again, it's not surprising, but it is a great target for optimization. And when it comes to optimization, especially for a library or an application like this, you really have two options. Either you could make it faster, or you could call it less. One of the other works. So the question kind of becomes what to do. How can I call find near letters less? And to do that, we came up, and by we, I want to give some credit to Todd from my Houston Perl Mongers group, and just the whole Houston Perl Mongers group. I did get to do this presentation once, and we came up with a bunch of ideas on how to speed it up. I'll give them a little bit more credit towards the end, but you know, props to them. Everybody should be part of your local Perl Mongers. But anyway, not all paths are fruitful paths. F, there were a lot of words that start with F. So that's a fruitful path. Let's keep going. FL, there are definitely more words. FLA, FLAG, flag is certainly a word, so I know that this is a fruitful path. There is no word in the English language that is spelled FLAGA. Well, once I know that, I don't need to try any of these. No matter how much I recurse or how much I change things, I will never find a word that's valid here. I've stopped right here. Once we've reached that dead end, stop executing. Abandon that path. Execute it fewer times. So how does it work? It's pretty straightforward. We read in a word list, and from that word list, we read in a hash ref, or I should say we construct a hash ref of 1 to n character strings. Now the n in that is the longest possible word that we're searching for. Okay? If I only need 4-letter words, it doesn't make sense to construct 8 letters word. It's a waste of memory and processing time. Then I just search the hash ref to see if FLAG, are there any words that start with FLAG? Yeah? Cool. All right, moving on. So that's what we do. I do have the code for that. I think it's going to be a little larger, so we might actually be able to talk about this. First off, it's just some boilerplate stuff. I read in the Word file. We open it. Okay. Then we process it word by word. And at the end of this, what we're doing is we're constructing the actual prefix cache, I'm calling it. The only thing I want to draw special attention to is this piece right here. If the word in the English language is only 3 letters, like all, for instance, I only want 3 letters. I don't want all nothing or all new line. It wouldn't quite do what I needed to. So that's why we're doing this substring piece here. When it comes to actually using the is start of word, super easy. I just check if it exists. All I'm storing are prefixes. And actually, I'll back up again to say, I'm not actually even storing words. I'm just showing a 1 if it just so happens to be a valid prefix. So when I search, all I have to do is check. Does it exist in the hash? Yes. Then this is a fruitful path to continue. If not, abandon the path. As for where we put this logic actually, we do incorporate it into find near words, and we do it right after the check for max word length. We just check is start of word. Easy stuff. Now, for check prefix, this is a much juicier flame graph. I like ones like this because it looks obvious. At the same time, though, you have to think about what you're doing. Just because this looks super ripe for optimization, it may not be. This is the load words method of the prefix calculation. It's got to do that spin up. It's got to build into memory this hash of prefixes. There is a cost to do that, but this cost is constant. It never increases. Okay? Well, for the most part. To go from a 4-letter to a 5-letter prefix, it takes a little bit more time, but really, you're talking fixed amount of time for this operation. As the search space increases, though, this won't grow. This will actually appear smaller as this grows. Okay? And I can see that load words was my most expensive in this specific case, because it was still small enough. And then find near letters takes up the rear, as we expect. Load words, constant, optimized by only building as much as needed. That's where I was talking about, where it's 1 to n, because if I don't need the extra letters, don't construct them in the prefix. Find near letters, we've done a pretty good job of find near letters. I mean, we'd have to get really, really creative to find some better way of just looking in each direction to find the letter. Not to say that there isn't one, because there's always some super brilliant idea that someone has where you're like, why didn't I think of that? But we would have to get pretty creative. Now for the part that I'm sure you guys have been really waiting for, the actual benchmark stats. Yeah, they're kind of readable. This is the 2x2 game grid. And in the 2x2 game grid, we're seeking a single 4-letter word. And before we get any farther, I just want to kind of let you see, this is the moose version, this blue line. The orange line is the pure Perl, or the Perl OOP. And then this gray line is the check prefix version. So we have all 3 versions up there. Now when we do this, I want you to just note the improvement by eliminating moose. I'm sorry, moose guys. I'm going to class on Thursday. So, but a cost. I still heart moose. Yeah. Okay. We do notice that check prefix has a fixed spin-up time. If you notice, we stay right around here. It's actually quite fast to find solutions, but it's not free to do that pre-work. You're going to see this have more of an impact as we go farther. This is a 3x3. In this case, the blue is the moose. I think I kept the colors the same. I'm not sure. The blue is the moose. The orange is the Perl object-oriented. And the gray is the check prefix.
What is this a part of over time?
This is each. Oh, thank you. I'm sorry, I wasn't more clear. The ordinate is the. No, ordinates are up. The x-axis are the actual levels, starting from the very beginning. They're getting cute, and they call them like frog 1 and frog 2. But for all intents and purposes, bottom row is levels, top row is time. And if we go back, that top line right there is, I think that's 0.012. Yes, is 0.012 seconds. And if we carry on here, that top line is 4.5 seconds. So that's what we're looking at. This is runtime for the different implementations. 3x3 game grid. We're seeking 2 words between 2 and 8 letters. Best speeds are realized when we have small lengths of words. Frog 9 and Frog 19, yeah, I know. That's kind of hard for you guys to see. Can I make this any more obvious? Okay. So this is Frog 9 to Frog 19. All of those are 4 and 5 letter words that you're searching for. This area right here are 4 to 5 letters. There's just different levels. You get an increase or a spike when the length of the word increases. Snail 7 and crab 12. So this, come on. This huge peak is snail 7, and this is crab 12. In those cases, we have 8 letters. And then you'll see similar spikes for crab 7 and frog 7. In that case, it's 7 letters. The question is why? And actually, this is an open question to you. I'm doing okay on time, so I can actually ask it. Why, and anyone's free to answer, why do these levels perform worse than those levels?
The search tree is much larger.
This is exactly correct. Because your search space is larger. You have to recurse more times. You have to go down 8 levels. In this case, you have to go down 8 levels. Compared to here, you only have to go down a maximum of 5. That is correct.
I'm guessing that you need to redraw the board after every word, and if you come to a stop
After every found word.
Right, and if you can't get to a full solution, you got to back up and start coming down a different path and restart the process of redrawing the board after the next word is found.
That is mostly correct. The only thing I'll change about that is I find all the solutions. I don't try each one individually. You know what I'm saying?
Okay.
Next, for the 4x4 benchmark, which is actually the one that's relatively significant and actually matters as it starts to get into the real game. At the very top, this line is 2,500 seconds. Okay, so quite a while. 2,500 seconds. So we did actually get fairly close to it with our Moose version. Okay? With our Perl object-oriented, we did a lot better. And with this implementation, so to let you guys know, that line right there is 500. So this is a 500-second line. Here, with our check prefix, you know, it's at least respectable, kind of. 2,500, nah. Okay? But here, we're doing okay. This is the 4x4 grid. What's different here is we're seeking between 3 and 4 words, or 3 or 4 words, and they're between 2 and 8 letters each time. For Penguin 1, 2, 4, 5, and 7, we have basically the same question that we're asking. We're doing okay. We got 4 minutes. We see Penguin 1. Actually, let's look at the significant one, which is Penguin 5. Penguin 5, I'm looking for 4 words, compared to Penguin 2, where we're also looking for 4 words. So here, the number of words we're looking for and their length also becomes significant, for the exact same reasons that were stated earlier. So, last, I think, 2 slides. So we're almost there, guys. I appreciate you bearing with me. There are 2 types of performance improvements that you can make. There are implementation details, such as the swap from using Moose to using Perl object-oriented. And then there are also algorithmic changes. And we're going to talk about the difference between those in a second here. Actually, let's do it right now. No, I don't want to do that yet. Okay, so implementation ones, you typically get some speed up from, but you're talking percentages. Maybe it's 10% faster. Maybe it's 15%. Maybe it's 30% faster. Okay? They help, but they're not going to get you all the way. When you make an algorithm change, that's where you start to see the multi-fold increase. Okay, so typically, you want to try to optimize your algorithms as much as possible. As for ideas for future improvement, I'm happy to take that question if you bear me. Yeah, I just want to make sure I get through. Implementation. A couple of things we could change. We could use Memowise. I actually tried initially to use Memowise, but well, first, for anybody who's not familiar, what it does is it trades space complexity for time complexity. So it just basically pre-compute. It doesn't pre-compute, it remembers. But you're just trading that, so you don't have to keep making the same function calls. The problem is, because we're using so much recursion, and because we're doing so much dynamic changing of things, this letter's now used, don't use it again, shift these over, it's actually really tricky to do it. And it drove me crazy initially when I was trying to implement this, because I would run the same test 5 times. Twice it would pass, 3 times it would fail. I literally thought I was going crazy. I'm like, it's deterministic, what's going on? Well, it turns out that the caching algorithm is not deterministic, and that's why that was happening. But, so it's possible, but it's going to be tricky. So, we'll keep it there. Another thing we could do is use Parallel Fork Manager. I know you could just fork naturally, but who's got time for that? There's a CPAN module for it. So Parallel Fork Manager happens to be one of my favorites. This would just spread the work across multiple processors, which would totally work, but it could get pretty expensive. Okay, sure, I use AWS. I could spot price something at like 25 cents an hour, which is sweet, but this is a pretty costly solution. And unless you're a hosting company, which almost all of us work for hosting companies, they have unlimited hardware, and that's why I like working with them. But anyway, next we have the concept of the algorithmic. We already implemented the check prefix, and we saw what a dramatic improvement that had. And I really want to thank Todd and the Houston Perlmongers for that idea. I mean, don't get me wrong, when it's my idea, I take credit all the way. But this was theirs, and I appreciate that. The next thing we have to consider, or you have to ask yourself, are there any other algorithmic improvements that could be made? Just something to ponder. I just want to conclude and say, first off, thank you guys so much. I know there's a million great presentations. I just appreciate you joining me. And really, I'm happy to answer any questions that you might have. Go for it.
So,
Yes, that's what I like to see.
so possibly if you ran the older version without any fixes for time on 100 by 100 grid, and then compare that with 100 by 100 grid, what were optimized program, you could find the difference between it, and then you could probably use that data for future projects.
I certainly agree that you could use larger and larger sets to find bigger and better trends. 100 by hundreds, you know, you'll probably take the heat death of the universe with this current implementation. But it's a great point. You need those data points. You know, you can't just walk in blind.
Actually, I think what he's talking about maybe is pre-computing, solving it kind of like chess solving.
Oh, that's an interesting idea.
What I wanted to ask you was how much have you looked into maybe optimal solutions to this problem?
I'm afraid I'm not quite familiar with the optimal solution as you're speaking.
No, I'm just asking if you've looked into, like, is there an optimal solution for this? And have you looked at kind of determine what the complexity of this algorithm is? Because I didn't really, like, get it completely. So it's hard to me. It's hard to quantify, but it seems like you probably do some deep work on reconfiguring the algorithm since it's graph-based.
I completely agree that the algorithm can be reconfigured, and I
But
think
have
there's
you know what the
tremendous room
complexity
for
is
improvement.
off the top of your head?
I do not. I would estimate it at somewhere around probably n cubed, but I mean it's probably n to the m or something like that. I'm more than happy to take more questions, but unfortunately that's the end of my allotted time. I'm not going anywhere, so I'm happy to step outside or hang around here and take more questions. But I gotta wrap it up. So guys, thank you so much. I really appreciate it. You guys are the best.